Good evening, and welcome to the Dublin Linux Developers Meetup. This month, we are meeting with Joshua Wood to talk about how is Openshift different from Kubernetes and why. Josh is a principal developer advocate at Red Hat, co-author of Kubernetes Operators and Openshift for Developers. He has worked in roles from system admin to CTO to build community with open source software. Josh, over to you.
Okay, I'll ask just for a quick confirm that I've actually got the right window selected and folks can see the slides. All right, diving in. I was a little confused by the window menu there, so I know OpenShift better than I know Zoom. Neil and I were just discussing as we did a little preliminary prep. So here we are. Welcome. Thanks for coming, everybody. We're going to talk about OpenShift and Kubernetes. Sometimes I call this talk the cutesy name from Sesame Street of my childhood. Same, different. We're going to talk about Kubernetes as the core of OpenShift and what OpenShift adds around that Kubernetes core and what the day two concerns are, why it tries to solve those problems. But before we can do that, we're going to set the stage by understanding why Kubernetes arose, what problems it's trying to solve, how Kubernetes solves those problems, and that is what the architecture is in place and the abstractions that Kubernetes uses to govern automating the operation, deployment, and running of distributed software. So I've already mentioned like the introductory bits about myself. The key thing I'll mention from this slide with my lovely face replicated on it is I was formerly at CoreOS. I was responsible for documentation there. The technologies that were acquired by Red Hat in the CoreOS acquisition prior to IBM's intern acquisition of Red Hat are the key driving technologies in OpenShift version 4 and up and how we deliver these features on the platform. The key piece of all of that coming out of CoreOS is this thing we call Kubernetes Operators. We're not going to talk a lot about operators today, but if you're interested in how we extend the Kubernetes API and the mechanisms that you can adopt from that pattern to automate your more complex applications or write your own APIs on top of the Kubernetes API, or deliver your software for running on Kubernetes clusters in an automated way with a lifecycle runtime manager monitoring your application all the time. That's what operators do. I've written a book about it with O'Reilly. It is called Kubernetes Operators. We'll have a link to it later in the slides where you can get a copy from Red Hat. More relevant to today's discussion, I also last year with my teammate at Red Hat, Brian Tanis, wrote a guide, an introductory guide that's closer to today's material called Openshift for Developers. This book, which we'll also have a link to later in the slides, is an excellent companion for step 2 after the stuff we'll be talking about today. Once you have a basic idea of what Openshift is, the Openshift for Developers book functions very similarly to some of the tutorials we'll link to, walks you step by step through building multi-tiered applications on Openshift from source code repo endpoints and deploying them on the platform, and then layers on as much automation of those basic activities as we can, and kind of shows you what the daily life cycle of a developer on OpenShift is like. So those are the 2 books. If after today's session you have questions that I don't manage to get to or run into problems with any of the stuff, the content and sandbox and tutorials that we turn over to you, you can always drop me a line by email at joshix@redhat.com, as you see on the bottom there. We've mentioned the developer sandbox. This link will come up a couple times through these slides. This is the same link you have in chat. If you'd like to sign up for an OpenShift cluster that you've got rights to experiment with, deploy things on, and take a look at all of the web console and stuff that we'll go through today, this is where you do that. So I managed to say no further ado and then did a lot of ado, but now we have arrived at the point where we can talk about what we're here to talk about. Why do we have Kubernetes? Well, this is going to be an outline of the agenda of what we'll spend the rest of the time talking about today. Why do we have Kubernetes? What problems is it trying to solve? What is Kubernetes? How does it try to solve those problems? What are the fundamental abstractions or API endpoints or data structures? And what is the executable code manipulating those fundamental abstractions to provide automation of deployment and scaling and failover across a cluster of multiple nodes, the basic function of the Kubernetes system. Once we've talked about what Kubernetes is trying to do and how it does it, we'll talk about how Kubernetes isn't enough. It's a little bit analogous to if you had just a Linux kernel versus the usefulness of a Linux distribution that has all the user land and the tools around it that you actually need to do useful work beyond day zero. OpenShift's relationship to Kubernetes is very analogous to RHEL's, Red Hat Enterprise Linux, distribution's relationship to the Linux kernel. Linux kernel is great. There's a ton of fantastic technology. A lot of bright open source minds have contributed to it over decades, but by itself, it doesn't actually do much useful work for a human being. It mitigates and manages computer hardware resources. To do useful work with the Linux kernel, you need this thing we call a distribution. User tools, command line tools, even graphical environments surrounding that kernel that allow you to issue commands to it, run applications on top of it, build applications on top of it, and manage those things over time. OpenShift similarly adds the things that we feel in our opinionated Red Hat way are necessary for day 2 and 3 and week 2 and 3 and the life cycle of developing of deploying and running distributed infrastructure like Kubernetes. So Kubernetes has arisen over the last 5 years, starting as a project at Google, growing out of their internal Borg systems, a paper I highly recommend you read if you want to get a grasp on some of the early design decisions that informed Kubernetes, is the Borg, B-O-R-G paper. We never saw Borg as software. It's never been open sourced. It's still used inside of Google. Kubernetes represents the open source projectization of the internal highly Google specific code. So in creating Kubernetes, there was an attempt to generalize these APIs so they would be useful outside of just the structures in place at Google, and to generalize the distributed computing ideas and discoveries, and especially SRE, site reliability engineering techniques that had been developed and arisen at Google in the effort to manage massive and massively growing distributed applications. One of the things that went along with, or maybe predated this pattern, and in fact inspired the need for something like Kubernetes, is a change in how we develop applications. We used to have this idea of a big monolithic application, quite possibly in a large shared binary, all compiled together, possibly even statically linked, that we think of as a monolith. And all of our application code went in there. That's can be complicated to maintain over time. And in response to that, first, there was an idea of internal modularity. That is, and you can see this reflected in necessarily single image programs like operating system kernels. The Linux kernel is still very much regulated by this idea of internal modularity. It is one large single linked together executable, the Linux kernel, but it has fairly clearly defined areas of responsibility within it, like the virtual file system, the memory management system, the RCU zero locking scheduling system for managing CPU resources. These areas are fairly well defined and modular within the kernel, to the extent that some of them are actually shipped as independent modules, but it's key to remember that when you load those modules, they get linked into that same memory space, and we're still dealing with a necessarily monolithic application. For years, we built our user applications on top of these monolithic kernels in really the same way. Then we adopted this kind of idea of internal modularity. As these applications scaled and the teams working on them, maintaining them, deploying them, and running them in production also scaled up, we looked for ways to make those designations of function and specialization of concerns represented by that internal modularity more formal and more like an enforceable contract. And so we started to see what you could think of as an external modularity, and that as it evolved, moved towards this idea we think of as microservices. Lots of small independent executables, not linked into a single memory space, communicating along network or other well-established channels via agreed protocols. and especially via APIs. So you can see this trend's fingers developing in several ways. There's the idea of REST applications in the web space. There's the idea of microkernels in the operating system space that reflects some of the same exact attempt to impose some contractual control and formal areas of responsibility on large, complex applications. In web applications served by distributed systems, we see this idea as this idea of a microservice. One job, one tool doing one job well, similar to the Unix tools idea, communicating with the other pieces of that application along well-established pathways so that multiple teams can more easily collaborate across the breadth of this large complex application, because changes in one of these modules doesn't require changes in the others, so long as the change module adheres to the contracts by which it communicates with these other modules. So that's all fantastic from a development strategy and tactics point of view. We've got a better way and more of something like a formal contract to regulate how these little pieces talk to each other, but it definitely led to a kind of proliferation. Instead of scheduling one app once or twice a month when we do new patches, test them, get them through the pipelines and deploy them, we want to schedule dozens or hundreds of apps, dozens or hundreds or thousands of times a day. Google's Borg system is making billions of individual scheduling, recovery, scaling up and down decisions in the course of a day, for example. So the microservices led to kind of a proliferation, both on the team side and communication side of source code and source code repos and needing to hand test pieces around. And on the system side of deploying and running these things, simply needing to deploy more things more often across more computers, vastly increase the complexity. And we look for ways to automate the deployment and management of all these new little pieces that we set up to make our development lives easier. Containers go along with this, because when we had all these little pieces, we really started running into the need to ship them around, whether we're sharing them to test within a team, whether we're deploying them to different systems that maybe have different libraries and dependencies in place, or whether we want to schedule them with software and move them around a cluster of not necessarily homogeneous nodes. The container gives us a single artifact with an application and everything it requires to run sealed within it. That gives me two very powerful things among a number of other features. The two that are relevant for us are, it lets me hand you a piece of application code that I've compiled, hand you that binary and run it without hearing me say, well, it works on my laptop. Because if I give you a Python application bundled in a software, an application container, you can run it on your Linux system, even if you don't have the same version of Python I have, because that's in the container with the application. Even if you don't have NumPy or whatever libraries I did imports or includes to build my application, they are also likewise within that container, within that application. In the same way, when I'm running an application on a group of computers that I call a cluster, I can naively ship that application in a container to any of those individual cluster members without worrying about if they have the dependencies I need in place, if they have the libraries or the version of Java or Python or whatever stack my application needs to run. That container represents a sealed artifact that has all of those dependencies in there. So I can move it around when a computer fails. I can restart it on a new computer when I want to replace a failed software object, an application that's failed. And I can move it to new computers when I want to scale it up horizontally to meet increasing demand without knowing a lot about what's in place on those computers beforehand, without making advanced arrangements to land my dependencies there. So microservices break down applications into more manageable pieces with defined contracts between them. That's a benefit for teams. Taking that same pattern and applying it to creating discrete objects that we call a container gives that same benefit to the systems that those teams are targeting for testing and for deployment. It essentially lets us pass these applications around much more naively than we can pass around, especially dynamically linked applications in the past, where installing an application or deploying it and running it means I've also got to go find all of its libraries and make sure they're in place. So I've already talked about some of these things. The key thing is the container is a software abstraction built on top of the Linux kernel, and it essentially is what you would get if you had VMs that instead shared a kernel. So it isolates the user land, the user's namespace, the process ID that identifies what processes are running. It isolates and provides a virtualized process ID namespace. That sounds really fancy, but you should remember when you think about these things that a container is actually just augmenting a virtualization that's always been in place in Unix and other modern operating systems. The CPU and the memory have always been virtualized, and an application has always believed that it had solo access to a large, sparse, contiguous memory space, which it in fact doesn't. That's an illusion the OS creates for it. Likewise, it believes it has all of the CPU at once, but in fact, the OS is time sharing it, switching it on and off, forcing it to yield the CPU, and granting CPU cycles to other applications that are multitasking with it. Containers atop the Linux kernel expand that virtualization to the file system namespace, meaning a process running a container sees a file system that is unique to its point of view and is not globally shared with the rest of the system. To the user namespace, my user ID within a container is unique to that container and could be duplicated in some other container running on the system. Networking namespaces and IP addresses, and this is a key feature. We have all these little containers, we're moving it around dynamically, software is managing that. If they provide a network service or communicate over the network, they need IP addresses and ports. If we don't virtualize that, we run out of them very quickly with this proliferation of application pieces, components communicating with each other. Containers let us virtualize that network namespace as well. So that's the basics of what we're dealing with. All of that proliferation led us to this desire for automation. And that's because we've got all these pieces. How do we scale flexibly and dynamically in response to rapidly changing demands? I just mentioned the thing about port conflicts that cause us to really benefit from the virtualization of the network namespace. How do I manage an application that needs to scale horizontally beyond a single host and keep it running with a lot of human intervention? Especially that lifecycle element. Just once I deploy an application, I would like to spend as little time as possible thinking about keeping it running if it falls over. I'd like it to get restarted automatically. I'd like it to get scaled up and down automatically, or at least within a very easy toggle of my fingers. I would like it to be able to, I would like it to be migrated around if an entire node, a system in this, a whole computer fails in our cluster of computers. And how do we then leverage all of that to automate deployment of new application versions? When you have all these small application components, and when you are satisfying customer demand by that velocity of shipping very frequently new features and fixes, applications are getting deployed all the time. The more of that we can automate, the more time we can save. And these are all the challenges that Kubernetes itself aims to resolve, and we could call these like kind of the first level challenges. Kubernetes is a Greek word that means pilot on a boat, or helmsman, the person steering a boat or a ship. You may recognize a word in English, governor, and especially the adjective that relates to that is things relating to a governor or a governor's office, gubernatorial. Those sound a lot like Kubernetes because they in fact descend through Latin from this Greek root. And that also gives you an idea of what the system does. It is an orchestrator or a pilot for running lots of containers and doing it at scale and with highly dynamic, rapid scaling, deployment, and failover changes, like we were describing as we were analyzing the problems and what Kubernetes is trying to solve. One of the side note here that's always useful is Kubernetes is open source. A whole lot of companies, Red Hat, Amazon, Microsoft, Google have contributed to it over the years and continue to do so. It is actually under the auspices of a foundation called the CNCF, the Cloud Native Computing Foundation. It's written in Go, and so many of its extensions, like we've touched on, operators, are also written in Go. but it can run applications atop it in really any language that you can package a binary in a container. So there's no limitation there for the kinds of applications that you run atop it. I would say that as a Red Hatter, the thing I see customers running on OpenShift and Kubernetes the most are Java applications, just to give you an idea, because they're so entrenched in the industries that we directly address. And a key idea out of all of this is that developers and ops teams, and especially as they undertake a cultural effort to understand one another's concerns and work better and more closely together, that thing we call DevOps, we really want to deliver a way they can manage and think about applications, not about source code repos, not about individual machines. We want to think of the cluster as a single resource. It's Kubernetes' job to make all those computers act like one big system. We have a single API we can address it through. We can declare our intentions and what we want to see in the world to that API, and let Kubernetes, the control plane, worry about making that happen. So that, again, our focus remains on the applications we build, which is where our teams deliver value to customers and to users. So how does Kubernetes do all of that? We're going to run through this really fast so we can get into OpenShift. I am looking at my watch, so I got some awareness of time here. We're going to talk quickly about the abstractions that Kubernetes defines, and then the control plane elements that manage those abstractions to yield the results of helping us with all of those challenges we just ran through. Okay, so the first thing that you're going to encounter in the basic unit of execution is the Kubernetes pod. This gets its name in a kind of winking sense from when Docker was the best known and primary container technology before containers were standardized into the OCI, Open Container Initiative, container image standard, of which Docker is a part, but there are now many implementations, different container runtimes that can run these things, produce these things, and they're interoperable between them. But Docker has this association with whales. Pods are a group of whales. A group of whales, they travel together. They're a pod of whales, especially orcas or killer whales. You see this term referred to a lot. What is a pod in Kubernetes? Well, we've talked about containers, and a container is an isolated element to ship things around. But we've also talked about how with a microservices architecture, container is often not an entire application, but rather a single component, one of several components that together function to serve the application's purposes. And for that reason, we have this higher level abstraction in Kubernetes called the pod. The pod is a unit where one or more containers executes. Within a pod, containers can share and in a specified regulated way can share things that Unix applications are typically used to sharing: System 5 shared memory, semaphores, network connections, and a view of the file system that containers on their own would normally isolate, and that between two pods are in fact isolated on a Kubernetes cluster. So the pod is your basic unit of execution. The best way to illustrate this is when we talk about scaling an application on Kubernetes up or down. If we're talking about horizontal scaling, what we're talking about is running more pods that replicate that same application and scheduling them on more of the nodes in our given cluster, so that a load balancing element that we'll come to in a moment can route between them and allow that application to handle an increasing load. So when we scale things up, we add pods. When we replace a failed application, that usually involves something that's failed and triggered, and either we as a developer or the control plane takes an action to delete a pod and then deploy a new pod or create a new pod in Kubernetes API terms. So the pod is your atomic unit and the thing that you're thinking about, like what runs on Kubernetes. What runs on Unix is a process. What runs on a container runtime is a Unix process packaged and isolated in the same way that we refer to as a Linux container. And what runs on Kubernetes is a pod, and that pod groups one or more of those containers together. That pod is addressable within the cluster with a single IP address, and that becomes important for how we build routing and load balancing as we move out towards the edge of the cluster, so that we can get traffic in and out to an application that we've already specified is dynamic. It's potentially being scaled up, scaled down, deleted, new versions rolled out, failed copies failed over and replaced with new running copies, potentially changing IP addresses all the time. That single IP address within a pod is what we'll build our mappings on top of, so that we have static endpoints to reach a service that can in turn then load balance among a really dynamic cluster of the applications that's actually answering those requests. And so all of that kind of is summarized by that last line on the slide, the idea of a shared life cycle. Everything in a pod lives and dies together. If I delete a pod, everything in it goes away. We do not typically delete individual containers if there's multiple containers running within a pod. The last comment I have on pods is, while I have seen interesting architectural arrangements that structure their applications, there may be more Kubernetes native, like by folks who are becoming really familiar with the platform and its patterns, or you'll see a pod that has 2 or 3 containers running in it so that they can deliberately share certain resources. The vast majority of running Kubernetes clusters I see at customer sites or through the telemetry that we have in Openshift are running one container inside a pod and kind of mapping one-to-one that idea of a unit of execution. So pods are then governed by another abstraction that we call the deployment, and underlying the deployment is this kind of secondary abstraction called a replica set. The key things here are when I deploy something on Kubernetes and I have one pod, I can tell it to scale to 3 pods or 5 pods. That scaling and that group of pods that are implementing one application horizontally scaled across our cluster are referred to in aggregate as a deployment. And underlying that deployment is a replica set. That is because if I have one pod and I run another copy of it, that second copy is a replica of that pod. They together are a replica set. If I scale it up to 3 or 4 pods, I have a replica set that has grown. My deployment describes that replica set and some of the other resources that go along with it in a single way, a single thing with a single handle. So from returning to that idea that we want to think about applications and not machines, deployments are usually that point at, or that handle where we are thinking about and manipulating application units. Now, we have a deployment, and Kubernetes can constantly be changing it for reasons we know, like automatic scaling, or even reasons that might be a mystery, where a pod fails and Kubernetes restarts a new one for us. A node could fail and an entire node's group of applications could be migrated by the Kubernetes control plane to another node in the cluster that has available resources. When all of that's going on, it can be a little hard for me to send a request across the network. Those endpoints are constantly changing. So Kubernetes has this abstraction called a service. A service basically uses labeling to point at a deployment and be able to route traffic, internally load balance traffic to one or more endpoints represented by a deployment, even as those endpoints change where they're running, what pod they're running in, and what IP endpoint they have inside of the cluster. So a service is 2 things. It is an internal load balancer when there are multiple endpoints providing a service named by that service. And second, it is a reliable, stable endpoint or name within the cluster to reach a service, even as pods live and die and are stopped and restarted, scaled up and down, and moved around among machines. If I know the name of a service and I'm running inside the Kubernetes cluster, I can use that service name to reach those endpoints, even if they've changed without my knowledge, and even as they change in the future. So the service is your stable mapping to a lot of dynamic resources. It's key to remember that that service is a name that is only known within the virtualized network space that exists in our Kubernetes cluster. In other words, a service name means nothing to external clients. And so we have this concept of an ingress in Kubernetes, and we'll come to this in a little more detail in Openshift, that we call a route, which is likewise a stable external mapping from outside the edge of the cluster to load balance to this service, which can then deliver to the dynamic endpoints inside of the cluster. So that's really kind of in a layer there, from service to deployment to pod, from the way we request some code run and do something for us, through the service to the deployment that keeps the desired number of those things running, scales them up and down when necessary, replaces them when they fail, down to the pods, the dynamic pods that are actually running code on individual computers within our cluster. I'm not going to detail persistent volume much, interest of time, but in the same way that we need to virtualize that network because we've got dynamic elements that need to send and receive traffic on it, we have a concept of virtualizing storage, persistent storage, so that as pods are stopped and restarted and scaled up and down, something like a database server can return to persistent storage that's actually on disk and maintained instead of the ephemeral storage that goes away and lives within the pod's lifecycle. And in that way, these are an abstraction that's similar to the service. You have some really dynamic, short-lived, ephemeral things, the pods that are running and getting scheduled. And then there are some abstractions that map them out to things that need to have a stable name so that they can be connected to across multiple sessions and not live and die with the pod lifecycle. And now, likewise, a lot of stuff, and the best example that we've been through already is services. Services are actually usually driven by this concept of labels, which is a very Google way to solve a problem if you think about Gmail, right? Labels and tags. But you can designate a label key value pair for any of these API abstractions that Kubernetes offers. And so what usually happens is a deployment routine will label an application with something like maybe its component designation. You might see component equals front end. You might see app equals application name, app equals web server. And those labels are then used in turn by that service so that it knows anything with that label is one of the items providing that service, so that even as IP addresses change, that service can always locate things. Likewise, developers use labels to organize components within an application, to label them so that they can take actions, say, on all of the resources that have a label X equals Y. You can kind of imagine what we do with these key value pairs as an organization and what do I want to say here, as a method of both organizing and giving imperative commands to groups of things that are organized by these labels. Now, all of this stuff is a lot of abstractions or data structures. Now we'll talk about the running code part of Kubernetes, the control plane. The control plane is a manager that watches all of those cluster resources that we've just described and more, the full Kubernetes API, in a loop, constantly checking that what is actually going on the cluster. Like, say I have a deployment and I have told it my desired state is for there to be 3 replicas of the pod that deployment governs running. The control plane is constantly running an observe, decide, and act loop, an OODA loop, to check my desired state against the real world state and then take actions to make the real world state match my desired state. So if I find that there's only 2 instances of my thing I've requested and desire to have 3 copies running, the control plane will take action, in this case, a really simple action, deploy 1 more, using its scheduler algorithm to find the node in the cluster that has resources where that application can fit. Now, when we go through the loop the next time, desired state is 3 replicas, 3 are running, and no action needs to be taken. The control plane runs that in an infinite loop and constantly monitors the state of the cluster versus the desired state. So when I want to make changes, I change the manifest representation, the description of my desired state, and then wait for the reconciliation loop in the control plane, whatever controller is implementing it, to come around and see that the desired state no longer matches the real world state and take action to make the 2 match, to make the real world match my desired state. The whole operators pattern is based on taking this simple model for simple stateless applications on Kubernetes of observe and act, and extending it with code that knows how to act on more complex applications that might need less naive, more arrangement to reschedule a failed node or get authentication assets to rejoin a cluster of, say, database servers or etcd servers that may be in turn running on top of a Kubernetes cluster. So it's just a hint of kind of what operators are and how you're going to see that we use them in OpenShift to extend Kubernetes. So you have a control plane, you have those 3 or 4 key abstractions that we ran through, and a number of other abstractions. Basically, you have a system for managing deployments on a large number of computers, keeping those deployed applications running, and potentially scaling them up and down in the face of demand. Now, that's all really cool, but as we mentioned before, it's probably not really enough. Let's look at a real quick illustration of this, because I just really like these slides, because I do think it helps to visualize the binary packing, the kind of resource management that Kubernetes and that control plane are doing when we make scheduling decisions on the cluster. So here we're looking at a cluster. We've referred to the computers within this Kubernetes cluster as nodes. A Kubernetes cluster is 1 or more nodes, usually more than 1, but it's very possible to run it on a laptop or just a single node for simulation purposes, or in edge computing scenarios where you may be very resource constrained, but you still want the benefits of the API and the automation and the tools and techniques you've learned. So we're seeing deployments of OpenShift and Kubernetes on really small edge computers, sometimes in single node configurations. But the usual situation is we're running some web applications on a number of computers, and Kubernetes is handling scaling and failover decisions for us. And that's going to look a little bit like what we'll see in the following. Let's talk about like with the scenario I was just outlining a little bit, scaling from the simple. Sorry, I was just checking the chat real fast. I'd hate if I missed everybody's questions. So it seems like we're going along all right so far. So let's talk about the situation where what we want to do is make scaling decisions. We're looking at an OpenShift screen here. You may, if you played with Kubernetes at all, be familiar with the kubectl scale subcommand that lets me make the same statement, which is adjusting that desired state. I currently have 2. I'd really like it to be 4. And in OpenShift, we can do that just by pushing some buttons. And when I pull up the web console, we'll look at that and actually do some scaling things. But what's happening on the cluster, I think, is helpful to visualize. So let's think about a cluster where we've got 4 Tomcat application servers running, serving 1 or more Java apps. And everything's nice, and they're running on our 6 cluster nodes. And Kubernetes is managing these nodes, and we deployed them with a kubectl command, or we deployed them on OpenShift as part of a project. We set that scale from 2 to 4, as we were just looking at. We've got all 4 of them running. And as sometimes happens to my software, I'm sure it never happens to your software, but to my software all the time, an application fails, and maybe it takes our whole app server down with it. Well, in the old way of doing things, like, we're now at a human intervention point. I've got to go try to maybe isolate and freeze this so I can troubleshoot it later, and also get a new copy running somewhere on that machine or on some other machine. But in the Kubernetes case, the control loop's going to come around and see that there are no longer the desired state of 4 running replicas, but only 3, and take an action. And you can see the action in this case found that there's resources down here on the bottom left that match the resources needed for our Tomcat server. And we can just schedule a new Tomcat server there, and we're back to the real world matching our desired state. To Nisa's question, we're really looking at, in my simple example here, this would be 1 pod on each node. And within those pods is 1 container running an Apache Tomcat server. Now, that if you know Tomcat at all, that's going to be a little bit weird, because Tomcat itself is then going to be running some applications and managing their scheduling to some extent. But it's the kind of software that you would see deployed with Java applications, is usually that application server or framework. Tomcat's maybe getting a little dated and long in the tooth to be on these slides still. There's Quarkus and Spring Boot and more of the modern frameworks that we'd probably see on Kubernetes clusters. But anyway, what we're looking at here is pods, 1 on each node. Now, those pods, as we talked about before, if it were a different application, might have more than one container running in them. But what we're scaling in that unit of execution in Kubernetes, and when we make a request to scale up or down, we're talking about scaling pods up or down and changing the number of pods. The important part of kind of looking at what we're looking at on these slides is really how Kubernetes makes a decision about where to place something by examining the resources that are available on the other nodes before making that scheduling decision. And of course, you have knobs and controls for your apps where you can say, I need a minimum of this much memory. I need a minimum of this much CPU share. It's a little out of our scope today, but it's good to know that those things are easy enough to regulate. And then some of the tools, OpenShift layers on top, are about making those things much easier to regulate and just giving them GUI dials and knobs where we can set our basic requests to tell the scheduler, only put me on a machine this big, and set limits that tell the scheduler to take action if I try to run away and consume all the memory and things like that. So there's a binary packing algorithm for making these scheduling decisions that Kubernetes uses to try to find a node that actually has the resources to support the application it wishes to schedule. So we can actually take these same techniques, and it's not really a different module or loop in the Kubernetes code. Those same techniques tell us what to do when an entire node in a cluster fails. Now, if you think about this from really large scale deployments, if you have 1,000 server cluster, you're going to have hard drive and machine failures on a multiple times per day basis, just based on the mean time between failure of the components we're using, right? So what happens when a whole node fails? Well, Kubernetes, again, is going to make some basic examination as the control loop goes around of our desired state, compare it to the real world state. We know that we were supposed to have each of these three things, a Postgres SQL Server, an Apache, and our other application running in pods, and they're specified, and these deployments should be on the cluster. When this node fails, the next time the control loop comes around, we know that they're not running, and we just simply use that same scheduling algorithm to go out and look for places where each of these can fit, and Kubernetes reschedules them on working nodes for us. And then we can address that node with human intervention or with the horizontal with the horizontal scaling automations that are, again, a little bit out of scope, but a way that in cloud environments, we can actually just add new nodes to this cluster out of kind of a reserve pool. So we've got all that stuff, and those are Kubernetes basics. Why is there an OpenShift? Well, because the Linux kernel is not something you can sit down and work on directly. You need Emacs and a compiler. You need a web browser. You need a spreadsheet application. Like, again, depending on the kind of work you do, there's going to be user applications and tools and tool chains that you actually need to do useful work. Kubernetes is like that kernel. It's a lot of brilliant ideas in there, but they're not necessarily very accessible. They're not real easy to use. And that's kind of what OpenShift's all about. And moreover, it's about extending Kubernetes with some opinionated choices about things you'll have to actually build and deliver software with modern techniques and kind of DevOps culture motivated teams. So there's this idea, first of all, at the simplest level, Kubernetes, you're basically going to address it with a command line tool, kubectl, and the Kubernetes web console, such as it is largely devoted to monitoring and looking at the state of the cluster with just a few handles for deploying things and adjusting things. OpenShift has a very full featured web console that has an application-centric point of view that integrates build facilities, a topology view of applications, operators for consuming other applications, and almost in the same way that you do cloud services, because an operator can automate, say, the running of a database cluster that your app in turn relies on. So you can select from catalogs and menus. And you have this really full-featured web console, which itself has a built-in terminal that you can use from the same place. So first of all, from a rookie developer sitting down, one of the things you get with OpenShift is kind of one-stop shopping in the web console for almost anything you're normally and routinely going to do on the cluster. And while we won't look at it today very much, that's also true on the ops side. There's an admin view for managing cluster resources themselves as opposed to managing applications that's kind of packaged within this web console rather than being a set of tools that you'd have to go out and add on one by one. Moreover, one of the key features is there is an OpenShift pipeline system that ships with OpenShift. Pipelines are the root and basis of a GitOps style of deploying applications from source code repositories, so that, and if you go, and I'll give you a link to a tutorial that actually focuses exactly on this kind of workflow, so that in the end, once you get set up, you can give OpenShift the endpoint of a Git repo on GitHub. OpenShift can introspect that repo even to find out what runtime, what language, what build tools it needs, build that application from source code, deploy it on the cluster according to your parameters and your desired state and scale, and then redeploy it when it's triggered by commits to your branch or whatever part of your source code repo, right? So within OpenShift, there's a piece you'd have to go out and add on to Kubernetes, and is an excellent illustration of the kinds of things that OpenShift includes and what makes it a distribution of Kubernetes, whereas Kubernetes is just sort of the core concerns. OpenShift is intended to be out of the box, usable, fully featured, ready to deliver applications. The pipelines inclusion is a great example of this, because these are what, if you took a vanilla Kubernetes and deployed it on AWS or GKE, you would then have to go look at the Tecton and Argo open source projects. You would need to look at Docker registry or Quay.io to provide a registry for your container artifacts after your build process has built them. All of this is included in an opinionated way on OpenShift out of the box. However, and this is sometimes important for some teams, we ship a pipelines. If you are not in a greenfield and you have a big investment in Jenkins pipelines or X, Y, or Z, or want to bring your own, because it's Kubernetes at the core, you have that same API, and any of those Kubernetes tools that you preferred over these, you can also map back in. So you have this kind of idea of, we've got an out-of-box tool, but again, it really is similar to a Linux distribution. And I think that analogy works really well, because if you go buy RHEL or download Fedora, with that operating system and its RPM repositories is nearly everything you would ever need to do useful work on a Linux computer. But if you've written your own financial management program in Fortran, you could run it instead, because the ABI is stable. If you can compile to that ABI, you can run your software there. The Kubernetes API and the operators and CRD, custom resource definition extension points, offer that same flexibility. So when we build this stuff around OpenShift, it's there and it's available. It's also not dictatorial, and you can plug other things in just as easily. We've talked a little bit about the web console. There's likewise a command line client, OC, that knows about things like build pipelines, image tags, other OpenShift specific features, and is the command line equivalent to kubectl for the core API. OC knows and understands the OpenShift APIs and the things that are a little bit different about them. So here's an idea, a real quick picture of the elements. In blue are these kind of core Kubernetes features that we've run through. And in red are OpenShift abstractions that are built either by extending the API with CRDs and operators, or by sort of unifying and setting intelligent defaults, which is the project, which is an augmented namespace that has built-in restrictions to a single user, has built-in defaults for resource consumption limits around a namespace. When you have multiple tenant clusters that multiple teams are using, the OpenShift namespace comes out of the box already configured with a lot of things that if you were doing vanilla Kubernetes, you'd have to make decisions and do configuration about resource limits and who has access to that namespace. The project is sort of like the namespace on steroids. Image streams relate a container image to successive versions of that image that are deployed as new versions are built, new features and fixes come in. We've touched on build configurations. Routes that you see at the bottom are again, Kubernetes has this idea of ingress for bringing network traffic from outside of the edge of the cluster inside of the cluster edge, and then letting a service deal with load balancing to the pods that provide that service. But ingress requires you to find a controller, which is really generally, there are going to be exceptions. Let's give a simplified version. If you want to build an ingress from scratch on vanilla Kubernetes, you have to specify the ingress and the rules for what network traffic should be able to traverse the edge in a YAML manifest file or a JSON manifest file. And you have to provide the so-called controller, which in most cases is going to be a web server, a layer 7 load balancer, to fulfill those ingress rules. And you got to do all that before you can get any traffic into the cluster. On OpenShift, OpenShift ships with HA proxy for layer 7 load balancing on the outside edge, and it ships this abstraction called a route that simply simplifies, builds a top ingress, but makes basic choices about those ingress rules so that when you're deploying an application, you can just click a switch or issue a single optional argument on a deploy command to OC and set up a route that routes traffic in from the outside without going and finding your own ingress controller. All of that stuff's already on the platform. So those should give like some ideas. We have not at all covered all of the things OpenShift adds. I don't have time to do that. But we have talked about some key ones, and I think more importantly, illustrative ones. The way the project relates to the namespace, as we've kind of gone through, sets up some intelligent defaults, kind of sets the RBAC with the expectation that this is going to be a multi-tenant cluster in a fairly large organization with multiple teams sharing it. Whereas the Kubernetes namespace, it's the abstraction and the right generalization you need to build that stuff atop it, but none of that is defined out of the box. Those are all second day concerns you'd have to answer if you were starting at zero from Kubernetes. So I think the project illustrates how OpenShift abstractions relate to the core Kubernetes abstractions. Likewise, I think the route, which we've described and which I've spelled out a little bit more on these slides so you can have some reference to them after our session, illustrate really well the kind of levels of one. There is an opinionated approach. Red Hat has made some choices about, well, if we have to have a layer 7 load balancer, we'll use this one, we'll ship it with the product, it'll be available, and there will be this route, this really simplified way of setting up its ingress rules. If you need more complex things, or if you need to balance network traffic at layers other than layer 7, like if everything that if you're writing applications that aren't necessarily just talking HTTP back and forth, if you got layer 4 apps or something lower down the network stack, because Kubernetes is there at the core, the whole ingress system and API is still in place. You provide your ingress controller for layer 4, you write your rules in the standard ingress manifest, and you can do that too. Those can coexist with routes, be used instead of routes. I think that's a really good illustration of OpenShift adds. It almost never restricts. Like we build on top of, we don't fork the core Kubernetes, we extend it through the designed extension mechanisms like custom resource definitions and operators. And that means that Kubernetes core is just as applicable and just as universal, or we're trying to make it just as universal as something like the Linux System 5 ABI and other really successful programming interfaces like that are stable and steady, and you know how to run things there. Because then when you build atop those things, you still have that core. And when the 1% of users who need more flexibility, that are really solving a problem that can only be solved through the more complicated method, like with routes and ingress, you can use route for your simple web apps. And if you're doing something way down the stack and trying to, God forbid, serve NFS or something here, you can provide your own ingress controller and go all the way back to kind of the core APIs. So OpenShift makes it easier for devs to get distributed system benefits, automated scheduling. It provides graphical interfaces for managing them. And then below this, I've listed some of the concerns. And because I'm so familiar with these concerns, I actually have already anticipated my slide a little. These are, when I talk to customers who maybe have made a choice not to use OpenShift and instead have gone a lighter weight direction with vanilla Kubernetes, or maybe one of the Kubernetes services from the cloud providers like GKE or AKS. I think it's AKS. They always change the name of things. Anyway, Amazon's Kubernetes service. They ask questions like, what about layer 4? You ship HA proxy and you got this great system for balancing layer 7 HTTP requests, but what about layer 4? What about other site-specific software-defined networking concerns where we have corporate arrangements or multi-site arrangements? You know, the opinionated case of routes doesn't really manage that, but routes being built atop ingress and the whole Kubernetes core still being in place gives you a way to answer those concerns. So those are kind of distinctions, advantages and potentially disadvantages or hangups, like where you might not want the added pieces. I always try to remind people, and if I get a moment here to do a little bit of demo, we'll look directly at, we're still talking about one API, the Kubernetes API. And by virtue of that, I can go over to a command line, and I will in a moment. We'll look at some kubectl commands, and then we'll look at OC commands. And when you restrict OC to the basic Kubernetes set, it functions exactly as any other client Go based application does, and talks to the Kubernetes API. Okay, so before I get into additional resources, I know I haven't left a lot of time, but I do want to just at least kind of blush through the web console in Openshift and some of the cool things about it. So kind of get that fella out of the way. We'll see what we can show you here. Okay, so I believe we should all be looking at the Openshift web console. I'm going to go ahead and get rid of the terminal. You can see this is the developer view, and you can see I've got one thing going on in my topology, and all I've actually deployed on this cluster so far is this thing we call the web command line, or the web terminal. So right within the graphical console, we can actually pull up a little container running of Linux userland for us. It's got the usual tools you would expect. In fact, you can inquire as to the underlying name of the kernel that container is being shown. You could even run top if you really wanted to. You can kind of see I have a Linux environment here, but it's actually running in this pod in a container on my Openshift cluster, and then I can interact with it again through the command line, but right here inside of the web terminal. Now I can do things that if you've done anything at all with Kubernetes, you're going to be familiar with. This will list all of the pods within my namespace. This little artifact is something that I think, because my network's a bit slow. There's a good clean version. So I can do a kubectl get pods, and it shows me, well, in this namespace or project that we're located in, I'm only running one thing, and in fact is the pod that provides this terminal service. Now, if I do the exact same thing with the OC command, you'll actually see the same output. Now I can do, so to show the opposite, here's an idea of, well, there's this thing called a project. We touched on it. It's sort of like a namespace on steroids, more ready for real corporate programming work by teams instead of maybe just an individual. It's got RBAC rules in place and isolation and resource limits. I can have OC list the projects on a cluster for me. But I can't, in fact, list all of the namespaces cluster wide on a shared cluster. But what I was trying to show here is that we can, even on an Openshift cluster, because it's still the Kubernetes API, projects are an extension to that API, but once they're there, they're a first-class member of that API. So even kubectl knows about these projects. What OC has that kubectl doesn't have is a suite of subcommands for manipulating and taking sort of bundled actions on some of these Openshift specific features. For instance, there's a suite of subcommands in OC for managing builds and build configs for building things directly from source code repositories, as we kind of mentioned. And those commands simply don't exist in kubectl. But as far as talking to the API, they're both client Go tools based on the same library. OC augments the basic kubectl functions for OpenShift specific operations. So that's kind of the web terminal and just like some real fast stuff on the command line. So if you're familiar with Kubernetes, you may be familiar with a command that looks something like this, where I give something a name for a deployment I want to create. I specify the image, the container image I want to run inside that container. And that would be how I would get something running. Well, on OpenShift as a basic developer, if I want to deploy a simple web server and I know where it is in my container registry, I can come over here. Now, Caddy is a real simple little stateless web server, HTTPD written in Go, that I like a lot, and I've got it packaged in a container and ready to run. But you notice when I typed in its fully qualified repository or container registry name with its version, OpenShift actually goes out to the Quay.io servers and validates that this is a container that's an OCI container that's accessible to me, pullable to this cluster, and is a container I can run, and actually validates that for me. Now I can do some syntactic sugar stuff where I can pick an icon that'll be represented by in our topology view, manipulate the name and the labels on it if I want. I'm just going to create a regular deployment. And here's the idea of routes. So when we're talking about, if I wanted to get traffic from the outside world into this thing, with plain Kubernetes, I'd have to write an ingress. I'd have to deploy an ingress controller, a level 7 load balancer in this case, to move that HTTP traffic from outside of the cluster inside of the cluster. In OpenShift, I have an ingress controller in the form of HA proxy already running. And I can, with this checkbox, say, yeah, I want there to be a route from the outside world to this application. And OpenShift will create that for me and return to me. Oh, I have to give it a slightly different name because I already created it. So now we have a Caddy 2. Now, Caddy's a web server. I chose to create a route, and we see that blue circle come around and show us our status that we're running. We can pull out the slide panel by clicking on its representation in our topography view. We get an idea of what pods are running. We can drill down to that pod and get information about what containers are running in that pod. We can look at resource consumption from that pod. We can look directly at the YAML manifest right here in an editor if this is a way we're comfortable making changes. I'm going to come back to the topology view, and like we can see that because I created a route, and I mentioned we get returned a generated URL that matches our cluster, we can actually open our web, open a web browser and make a request to our web server and get our request answered by our container that we just deployed in a pod, mapped to a service, and created a route to deliver traffic in from the outside world. I'm going to wrap up. I know I've gone way over. I just am always super excited to show some of this stuff to folks. One of the last things I want to show is the administrator view in this web console, and something really cool about OpenShift, which is this idea of a vast catalog of Red Hat partner and open source, project operators that provide services and applications in a way that once you're selecting these things from the catalog on an OpenShift cluster are very much similar to consuming cloud services and SaaS type services. So if my app needs a database, I can come here into the OpenShift operator hub and select a PostgreSQL database like those Crunchy provides, MySQL, MariaDB, Cockroach, Mongo, lots of databases. And the operator manages that database or database cluster like a software service for me. And as the application developer, I really pretty much just worry about gaining access to its endpoint and its authentication information so that my app can use that backend service. There's operators for middleware like message queues and Kafka, operators for a vast array of stuff that is sort of foundation software on which other software is built. And you can directly access those things and use them very much like a service with the operators pattern, Kubernetes operators extending OpenShift to add those features and automate management of complex applications like that. So I love doing, but I actually want to switch back over here and point to oops, the developer sandbox. That's what I was just using. If you liked what you saw there, you can sign up. Red Hat's going to want you to register for the developer program. It's free. They're just going to want your email address. I believe you can even opt out of any marketing emails. You get access to namespace on an OpenShift cluster. You'll have access to it for 30 days. It can be renewed at the end of that 30-day period, and you can play with all of this stuff. The little bit of demo I was doing that I barely left any time for there at the end was all on an OpenShift sandbox cluster. This link will take you to a step-by-step tutorial on Red Hat Developer that you can perform on that cluster. It'll really show you how to set up a GitOps pipeline, build an application from source, and have it be automatically deployed each time you commit changes to that source code repo. Likewise, there are more tutorials at developers.redhat.com. In these slides, which I will work to make sure are available to you folks afterwards, you can get a free copy from Red Hat of our book, OpenShift for Developers, my colleague Natalie's book about porting and modernizing Java applications for these cloud-native platforms like Kubernetes and OpenShift. There's a few other books. I know I ran long. I just kept going because nobody yelled at me. So hopefully everyone's still here. And now I'm going to try to take a couple questions. Nisa, that's a good question. And yes, we now call, so Minishift's a funny story in Red Hat, just because it's been around forever. It remains around and very useful, but we keep changing its name so that no one knows where it is or where to find it. Minishift for a while was called Code Ready Containers and is now called Red Hat OpenShift Local. But the upshot is if you go get Red Hat OpenShift Local, you will have the web console, just as we were showing in the sandbox, and as we would show on any other. OpenShift is likewise available as a managed service from Red Hat, as a managed service from Azure and AWS as catalog offerings. So that you can directly get OpenShift as opposed to going to like EC2, speccing a fleet of machines and then installing your cluster manager, Kubernetes or OpenShift on them. You can go to many of the cloud providers and consume OpenShift directly. Azure especially has worked closely with us at Red Hat to make that service available. We have a number of customers who consume it that way. You can run it on obviously your own data center. And last but not least, OpenShift, which we call OCP, the OpenShift Container Platform. Like RHEL and Fedora, there is an upstream open source project from Red Hat that is available to everybody with no support and no branding, but is the upstream that we call OKD, the OpenShift Kubernetes distribution, that represents all the bits that eventually go downstream into the product form, the OpenShift Container Platform. They all have the web console. They all have operators. They all have everything that I've shown. I'm trying to think. There's a few things like Minishift, which I always still call it as an example of one thing. Will the out of the box OpenShift Local Minishift, for reasons that it already is it's a pretty big application, Kubernetes and all this stuff to run on most single laptops, and we ship it by default with most of the metrics stuff, the graphs and resource displays and Prometheus based metrics and monitoring stuff that comes with OpenShift. We ship Minishift or OpenShift Local with most of that turned off, but there's very simple instructions at the OpenShift Local websites for turning it on if you've got a laptop with the resources to support it. And likewise, in a similar way, OKD, the upstream, is all the bits that are eventually in OCP, but they obviously don't come with support or consulting or training or a guaranteed schedule for bug fixes and all of the stuff with that we ship with the actual product. So folks, I hope that was useful. I think I'm actually like 20 minutes long over the whole event. But I suppose everyone was free to leave. They were really bored straight up at the noon time. So I hope that that's a high level glimpse and showed you some of the things and maybe made you interested in OpenShift. And even if it didn't, I hope it revealed some of the underpinnings of Kubernetes and what is and isn't there when we talk about Kubernetes.